Hello, everyone. I'm Boyuan from University of Pittsburgh. It's my pleasure to present our work, Eavesdropping user credentials via GPU side channels on smartphones. This is a joint work with my lab mates, Ruirong, Kai, advisor Dr. Wei Gao, and Dr. Jun Yang at University of Pittsburgh. The theme of our paper is that GPU on mobile phones could bring important security vulnerabilities. When the GPU hardware is shared by the malicious app and victim user apps, information of these victim applications may be eavesdropped through side channels. Foreground user activities result in changes in display rendering, which in turn produce different amount of GPU workloads. Such changes of GPU workloads can be measured by background eavesdropping apps to infer sensitive user information of activities. There are multiple ways of measuring such GPU workloads, and in this paper, we particularly target performance counters. We will later show that some of these GPU performance counters have strong correlation with user inputs and can hence be used to infer these sensitive user inputs. Our goal is to design a side channel attack to eavesdrop sensitive user login credentials, such as username and password, from unprivileged background apps. Here is a simple demo showing how this attack could work. For example, when the user is typing their username and password in Chase mobile banking app, the eavesdropping app running in the background will capture the screen display changes of the on-screen keyboard when the user is typing, which are measured by GPU performance counters. Such info is then analyzed to infer such input credentials and transmitted to the backend server. Compared with existing works that are limited to coarse grained inference of user activities, such as specific app being launched or the website being visited, this attack poses more severe security threats to smartphone users. We build this GPU side channel through reading the value changes of GPU performance counters and correlating such changes to user activities. GPU performance counters, or GPU PCs, are groups of hardware registers that stores resource usage information of individual GPU hardware components, such as bus, GPU cache, computing units, etc. Among all kinds of GPU PCs, we focus on counters about user interface layouts and display, which are strongly correlated with the eavesdropping target or current screen contents. We target on correlation between key press pop-ups and related GPU performance counters. During typing, such key press pop-up helps the user to determine whether the correct key is being pressed. Such animation of key press pop-ups create a noticeable amount of display changes that can be captured by GPU PC value changes. Such value change is repeatable since the same animation will take place for the same key typing. It is also differentiable since different keys trigger different GPU PC changes. It is because of not only the unique positions of each key on screen, but also the unique GPU workload during rendering due to GPU overdraw. With different UI components on different layers, the GPU will render all components in a back to front order. In the bottom left figure, 3 objects are rendered in 3 layers. The blue bottom part is rendered first, followed by red part on layer 2 and green part on layer 3. Some pixels and tiles are rendered for multiple times on different layers, causing GPU overdraw, which reflects to a certain amount of extra GPU rendering workload. This example with highlighted tiles comes with 3 times of GPU overdraw. On a typical on-screen keyboard app, such as Google Keyboard, the keyboard UI is rendered in layers. The pop-up animation is always on top of other keys. Pop-up for different key pressing events trigger different amount of GPU overdraw based on surrounding keys and their positions on screen, making it possible to do classification on user inputs using their corresponding GPU PC value changes when different keys are being pressed. Specifically, we target on these three categories of GPU PCs that reflect GPU overdraw. We find that for on-screen keyboards and pop-up animations, 3 GPU PC value changes will occur sequentially with 1 key press event. Once a key is pressed down, the pop-up hint will cause changes to related GPU PC values. After the user releases the key, the appearance of text echo in the text input box will result in another value change. Immediately after the text echo, the disappeared pop-up will then incur the third change. We can set up a unique key PC value mapping for given device model and on-screen keyboard software setup. This forms the basis of keyboard input classification and inference. The bottom right figure shows the mapping between the value changes of 2 GPU PCs in the RAS and LRZ categories and 26 alphabet letters. With similar approach, we can set up a classification model to recognize all the character inputs in the on-screen keyboard. Based on these insights, we design an attacking system as follows. The whole system consists of 2 phases, an offline training phase and an online attacking phase. In the first step, the attacker uses their own device to collect GPU PC data and construct an input classification model based on the collected data. This trained model, along with the eavesdropping code, is then embedded onto an attacking app as malware. When the attacking app is ready, it can be distributed through the App Store, such as Google Play, or published individually as APK files on the internet. Once the attacking app is installed on victim's device, the online attacking phase starts once the user launches the app. The malicious app will launch a background service to keep querying the GPU performance counters in the background in order to monitor user activity and infer any user keyboard inputs using the classification model built offline. The eavesdropping results can later be sent back to the attackers through the internet. Our research focused on mobile devices with Qualcomm Snapdragon SoC being used on Android devices. On this platform, the name of all available GPU PCs can be queried using GL-AMD performance monitor extension from OpenGL-ES graphics API. Based on this name string, the functionality of each GPU PC can be roughly guessed. To retrieve the global GPU PC values, we utilize Qualcomm's kernel graphics support letter interface or KGSL interface to directly query their values using IOCTL system call. Since this is a standard Linux OS call, its access is explicitly granted to any unprivileged apps. Doing so then circumvents any permission control enforced by either the OpenGL library or the Android OS and provides fast and convenient access to actual GPU performance counter values. In practice, there are multiple system factors that need to be solved to reach a high inference accuracy. The first group of factors are inaccurate GPU PC value readings caused by different reasons. In some circumstances, key press rendering may repeat in 2 consecutive frames, causing duplication in PC value changes, like the second key press in the frames. When the sampling of PC value happens before the frame rendering finishes, the PC value change may split into 2 consecutive samples, like the third key press in the figures. Many other system noises may also happen randomly due to various system UI changes, such as cursor blinking, system notification, animation, etc. Besides inaccurate value readings, human behaviors also brings difficulties in input inference. For example, the eavesdropping app needs to identify app switching events in order to determine current foreground app. On the other hand, text deletion using backspace key also affects the input inference. To tackle with possibly inaccurate PC readings caused by value split, value duplication, and random noise, we propose an online searching algorithm. We use this example to demonstrate how the algorithm works. First, if the reading at time 6 is considered as a valid key press, then the next reading at time 7 with a sliding time window nearby, it will be considered as invalid to eliminate any possible value duplication. Second, readings at time 9 and time 12, they are too far away from any pre-recorded values during the offline phase, and hence they are considered as system noise. Third, for the value at time 13, although it does not correspond to any pre-recorded value, we further seek to see if there are any other PC value changes within the time window. If so, we can combine these values and verify if the corresponding values is a value split. In this case, the sums of values at time 13 and time 14 reflects a valid key press. During input, user may make corrections using backspace key. To detect such human behavior, we use the fact that some GPU PC value changes are linearly proportional to the text length in the input box. As you can see in this example, the beginning PC value changes at time 1, 2, and 3, they have a constant interval of 0.5 seconds, which reflect cursor blinkings. The values at time 4, 5, and 6, they reflect the text inputs and have increasing PC values. As such, with the values at time 9 and 10, they decrease, we know that they correspond to backspace presses. In real scenarios, the user may switch to other apps at any time and switch back to the original app later. To detect such scenario, we find out that GPU PC values near the end of app switching procedure comes with strong feature of repeatedly generating the same value. In our case, we locate the switching event when there are 4 or more same PC value changes occurring, and with the interval between each change to be less than 50 milliseconds. Using this feature, we can detect the app that the user is going to use and determine whether the current foreground app is our target app. We implement our system in 2 parts based on the 2 phases. For offline phase, the data collection is done with rooted Android device that connect to the computer using Android ADB debugging connection. Scripts written in Python help to emulate key press events on smartphones and collect GPU performance counter data. The data collection is controlled from the computer. Collected data are later processed and generate models for use in the online phase. For online phase, we build an Android app that emulates our eavesdropping program written in C++. The eavesdropping result is then displayed in notification bar or silently sent out using internet. As shown in the figure below, we are able to achieve a high inference accuracy of individual characters of up to 98.3%. For text input of different lengths, the average accuracy is 81.3%, which means that around 80% of the inputs can be correctly eavesdropped without need of further guesses. This is important for eavesdropping sensitive user credentials, such as passwords, where the total trial numbers are limited, such as maximum of 3 attempts before the account gets locked. We also evaluated the inference accuracy under different setups, such as different on-screen keyboards and different target apps, We find out that most commodity on-screen keyboard software are vulnerable to our proposed attack due to the keyboard pop-ups, and the inference accuracy is not impacted by the choice of keyboard and target app. We repeat the whole experiment on different devices with different setup, such as devices with different GPU models, the same device with different screen resolutions, and same device with different Android OS versions, etc. We find out that our proposed attack is applicable to all tested Qualcomm Android smartphone devices, as long as the classification model is retrained for each device setup. The storage space for each classification model is also small enough, which is 3.59 kilobytes per model, to allow the Eavesdropping app to cover most popular Android models. In this paper, we also discussed several possibilities to mitigate this attack. The most viable mitigation would be enforcing GPU PC access control. With the help of Android's SE-Linux framework, the Android OS may allow or deny fine-grained access to certain system resources by the requester's role, such as unprivileged apps, system apps, etc. This is called role-based access control, or RBAC. One possible approach is to filter IOCTL system calls and deny access of unprivileged apps to the global GPU PCs and allow access for privileged apps and system processes. Regarding the vulnerability disclosure and the official mitigation, we keep in contact with Android's security team and was informed that a patch will be provided in an upcoming Android security update. To summarize, we identified GPU performance counters as reliable hardware indicators of users' key presses and quantified correlation between GPU PC values and key presses. We also designed a system to allow unprivileged attacker to read global GPU PC values on victim device. Finally, we quantify and mitigate the impact of various system and user factors to achieve a high key press inferencing and eavesdropping accuracy. For more details, please refer to our full paper. Please feel free to reach us if you have any questions. Thank you very much for your listening.